What is a real image? One of the most familiar is the real image that is formed by an overhead projector like this one. In this particular case, the real image is formed by a glass lens rather than a mirror. A light source under a glass screen illuminates an object, in this case a piece of film with a picture on it. From any point on this object, light rays diverge in all directions, many striking the lens overhead. The lens causes these rays to converge. A plane mirror in the instrument does nothing but conveniently change the direction of the light rays as they converge. At the point at which these rays converge, any form of surface placed in the path of the rays, whether a proper projection screen or a simple piece of paper, will show a crisp, real image of the original object. So, if this image is real, then what happens when the image is not real? Imagine you are looking at the reflection of a person in a mirror. The image of the person appears to form behind the mirror. But light from that person, the object, does not in fact pass through to the other side of the mirror. If you place a screen behind the mirror hoping to capture a real image of that person, you'll be disappointed. There are no light rays from the object behind the mirror, and no real image there. A virtual image is the name given to an image like this that is not real. The geometry of light rays can be used to explore the position of an object, which, in turn, will influence the magnification of the image that is formed, as well as the attitude of the image. Geometric optics can determine whether it's a real image, or, as is always the case with plane mirrors, a virtual image. An object reflects in a mirror. Where will its image be formed? How large will it be? What characteristics will it have compared to the original object? The geometry of optics can be used to answer these questions. The simplest of all mirrors is a perfectly flat, smooth, plane mirror. Rays from a single point on an object diverge in all directions, some striking the plane mirror. They reflect, but continue to diverge. By contrast, when a piece of film is placed on an overhead projector, light rays diverging from a single point strike a lens, which causes them to converge again. After being redirected by a conveniently placed plane mirror, these rays continue to converge. At the point at which the rays meet, a real image will form on the screen. But where is the possibility of convergence here, using a plane mirror? The image appears to be behind the mirror. It is a virtual image, not a real one, because no rays from the object reach behind the mirror. Whether converging or diverging, there are simply no rays there to appear on a projection screen. How then can optical geometry help predict the position and apparent size of this virtual image? The answer can be found by ignoring the barrier formed by the mirror and extending each reflected ray back from the point of reflection. These lines are usually shown as dashed lines to indicate that they are not themselves rays of light. Take a point at the top of an object. Draw diverging rays to the mirror, where they reflect and continue to diverge. But, extending the reflected rays back behind the mirror, the extension lines will converge. The point at which they meet will be at the top of the virtual image. It's only necessary to draw a pair of rays to find the point where these ray extensions meet. A similar set of rays from the bottom of the object strike the mirror. Extending two or more of them behind the mirror will define another point of convergence at the bottom of the image. From the handle of the coffee pot, yet another pair of rays is drawn to strike the mirror. Extending these rays behind the mirror gives us the placement of the handle on the image. And in the same way, we can place the spout of the coffee pot on the image. Drawing rays in this manner defines four distinct properties of the coffee pot image. We can determine the apparent position of the image from the mirror. We can determine the apparent magnification of the image in relation to the original object. We can determine the attitude of the image. It is the right way up. And because we extend the reflected rays backwards through the mirror, where these light rays do not actually travel, we are defining a virtual image rather than a real one. Drawing and studying light rays, we can also gain a better understanding of one puzzling peculiarity of plane mirrors. Left and right-hand sides of an object are reversed in mirror images. It's instantly noticeable when we try to read a word or a line of text as it reflects in a mirror.